LLM hallucination is probably the #1 problem in the AI research right now. So why do LLMs hallucinate? The main reason for that is that LLM knowledge itself is limited. So you cannot actually train large language model to have unlimited knowledge. Once the model is trained, during the inference time, the LLM model weights do not change. They answer your query based on the knowledge that is embedded in the model weights. Moreover, to answer your queries, LLMs need context. This context you basically provide in a prompt, for example, or you even just get it from external knowledge sources and somehow you put it in the context window of the large language model. The problem, however, is the context window of the large language model itself is also limited, so it cannot embed all the knowledge that you have in an external knowledge source, and therefore the LLM will hallucinate. So for example, when you ask a question, the answer is not in the context, nor in the knowledge of the model. The LLM is sometimes prone to giving you false information. That's what we call hallucination. How to actually bridge this gap? How to connect the external knowledge of the real world with the LLM? One of the most common solutions for this is what's called RAG, Retrieval Augmented Generation. So Retrieval Augmented Generation, as the name suggests, is retrieving or selecting some parts from our external knowledge and giving it to the context of the large language model. So here's how it works. You would have the input documents, the external knowledge that you want to give to the access to the LLM. You actually then split it. So you create chunks. So you split it into chunks just for easier processing. And those chunks then go through a vector embedding model. We convert natural language simply into vectors. And those vectors will facilitate easier semantic similarity search. After we have all these vectors, then we put it in a vector database and in an index. So basically we sort them in a way to make this similarity search very fast and efficient. So now in the query time, once we have a user query, we also vectorize it. So we turn it itself into a vector, and then we retrieve the top K chunks that match our query. And then we put it inside the LLM context, and then we generate the answer or the response based on the user query. So this is how retrieval augmented generation works. There are a couple issues with this. First of all, traditional RAG does not have a holistic overview of our dataset. For example, if we ask what are the top themes or what are the top products in my store, the large language model will take this query as it is, top products in my store, and then we run the similarity search against our vector database. And the top K chunks or the top K vectors will have terms like products, top, store. It will only retrieve a flat set of documents that basically are as semantically similar as possible to the query itself. And therefore, it's not going to capture a holistic overview of our top products in the store, for example. The second issue with this is that it doesn't capture details and nuances and relationships between separate entities and separate documents across our vector database. So some vectors might be related to each other, but this relationship will be completely ignored during the vector search, and therefore we will miss some context and some data that is important to answer the user queries in some cases. So these are the two main issues with traditional RAG. And to solve that, GraphRAG has been introduced. So what is GraphRAG? As the name suggests, it's a retrieval augmented generation that is based on knowledge graph. So instead of having a flat set of documents, now we have a knowledge graph to store the documents and the relationships between entities in our dataset. So the first step for this is to actually build the graph. And then during the inference, we will search through and traverse through this graph to get as much high quality of a context as possible. So let's see how this works in practice. So first we have the indexing phase, and after that we have the querying phase. So during the indexing phase, first we have our raw text files or the raw dataset that we want to index. After that, we split this raw dataset into documents. So we also split it into chunks, the same way we did in the traditional RAG. However, now, instead of building the vector database directly from these chunks or creating the vectors directly from these chunks, what we do is we first extract entities and relationships from these chunks. Entities are actually like places, names, geographic locations, and those will be the nodes in the graph, and the edges will represent the relationships between these entities. So for example, Berlin is the capital of Germany. So the relationship is a capital, one entity is Berlin, the other entity is Germany. There will be hundreds and thousands of these relationships in the dataset, or even tens of thousands and hundreds of thousands of these relationships that will form then a graph. So after we have this initial graph, then we will do graph pruning. So the pruning will just is just to remove the noise from the dataset. It's basically to remove concepts that are, or entities that are insignificant in our data, and it's highly unlikely will be useful for searching or for answering queries from this dataset. After that, we do hierarchical clustering. We now group nodes, we cluster nodes that are semantically similar to each other into communities. And we do that into multiple levels. So larger communities embed more dense knowledge in our dataset than lower level communities. So now after we have this hierarchy, what we do is we do community report generation. We run LLM summarization across the communities. So we basically create summaries of the communities using the large language model, and these summaries will then be vectorized and stored in a vector database. So now instead of having just a flat vector database, now we have a hierarchical, multi-level knowledge of the database, taking into consideration the relationships between entities as well. So now this is during the building time of the graph. So after we have built the graph, this is how it's gonna look like. So I've built that using GraphRAG from Microsoft, the official implementation. So as we can see here in my graph, there are basically the communities are semantically grouped into colors. So for example, the green color in this case is the geographic location. For example, here we have Andorra, we have Spain, here I have Denmark, here I have North Macedonia, here I have Norway. So the green basically represents geographic locations. The pink one or the purple one, they represent events. So for example, let's take the GDP event as an example, and let's see what is it connected to. So for example, it's connected to Lithuania, so it's connected to countries. At the same time, it's connected to some other events. For example, Gini index coefficients. It's also connected to this concept, which is imports of goods and services. So importing of goods and services is highly semantically related to the GDP. So now we have this knowledge graph that embeds this knowledge about our dataset. So next, how do we actually query and build context using this graph? So first, the user query comes, and during the initialization, we do query processing. So we might also need to create a vector from the query itself, and we select the search strategy. So here we will see two main search strategies. First, we will load the tables, and we will load the vector database itself of the community summaries and the entities and so on. And here we have two main strategies for search. The first one is the global search. This is like for global concepts about the dataset. For example, as I said, like what are the top products in my store, or here in our case, in my knowledge graph, is like what are the main countries in Europe, or what are the main political systems in Europe. So at the beginning, there's going to be a map stage. So this will take the batch community reports. They're mostly related to our query. So for example, the political systems. And then after that, it's going to run a reduce process, a reduce stage. In the reduce stage, it's going to only fetch the reports that make the most sense to answer this query. And then it's going to generate the global answer. So the global answer, it basically has this top level understanding and holistic overview on the dataset. The second type of the search is the local search. So during the local search, we take the query and then we do entity mapping. So we map the query using also semantic similarity search with the entities that are similar to this query. For example, this is for asking specific questions like, for example, what is the capital of Germany? When I ask what is the capital of Germany, the most semantically similar to this query is going to be like Germany and the word capital as well. So after that, we gather the context. We look at the entity text units, the relationships, and also the community summaries that this entity belongs to. After that, we build the prompt. So we do the prompt construction using all the information that we gathered from the graph traversal and from the relationships and from the community that it belongs to. And then we build the context. Now we give it to a large language model to summarize the final answer for us. So now, after we have seen how these both algorithm works, now let's actually see a live comparison, a side-by-side comparison of how they actually work. So I have built this side-by-side comparison, and now I will show you. So for example, here I have this query, describe the political systems across Europe, and here are the results. So the traditional RAG answered me, okay, types of political systems, authoritarian regime, Belarus, parliamentary republic, Greece, federal parliament, Belgium, federal public, Germany, and here it gives me a summary. So this is actually a good response. However, it have fetched information related to specific countries. So it lacks somehow a holistic overview on the dataset. While let's see how the global search answered, for example. So the global search gave us a more higher level overview about the systems. not directly related to countries. So for example, types of political systems, they are parliament systems. Countries such as Germany and Italy operates under this parliament system. Semi-presidential systems, democratic and social democratic influence, political dynamics in Eastern Europe, Northern European stability, unique governance, smaller nations, and it gives a conclusion. So we can see it's like a higher level understanding of the nuances of the dataset itself. So now let's see how the local one answered. So the local one answered parliamentary democracies, presidential systems, constitutional monarchies, civil law systems. The traditional RAG gave us just examples from different countries about how the political system operates there, while the global and local search give us like more high-level understanding and more nuanced answer as well. So now let's run one more demonstrative query. And this query is, what are the cultural similarities between European nations? This query is challenging for traditional RAG because it looks at the word similarities. It might be able to get traditions or like cultural traditions or like cultural themes of European nations separately, and then it's going to look for the similarities based on the results. So the LLM will do the similarity matching, but the search itself or the retrieval itself doesn't take into consideration the word similarities at all. Here is the result of the traditional RAG. So the cultural similarities between European nations, we have shared cultural heritage, okay, world heritage sites, natural landscape, economic structures, linguistic and religious, okay, commonalities, and many European countries observe a dominant religion, for instance Poland, Roman Catholic, social factors, okay, that's actually a pretty good answer. Let's take a look at the local search. A multitude of languages, many of them belong to the same language family, such as Romance and Germanic languages. So the GraphRAG again gave us a holistic overview of the languages in Europe, while a traditional RAG only mentioned Poland and Slovenia in the documents, and therefore it only captured similarities, only like talking about Poland. So the global search also gave us the same answer, which is also good. And so this is basically the side-by-side comparison that tells us why GraphRAG is much better in building the context over a dataset and capturing these relationships between entities and in giving us this holistic overview on our dataset. However, this comes with a cost. So as we can see here, the time for the traditional RAG took 17 seconds, while the time for both local and global search combined is 57 seconds. So it's almost like 3 times the cost, the trade-off between the quality and the latency in our system. So this will depend on the use case that you're building. But we can see clearly that GraphRAG excels in building a much better context to answer the query. So next, this is first solution to our hallucination problem. Now here we're introducing another solution to the hallucination problem, which is self-RAG. As the name suggests, self-RAG is when we make the model self-reflect on its answer. So after the context has been built, and after the query has been answered based on this context, then we ask the large language model or a separate agent or a separate large language model to compare the context to the answer and found any discrepancies or inaccuracies in this response. So does the response have information that does not exist in the context? If the answer is yes, then this information might be hallucinated, especially in cases when we want to force the LLM to use our knowledge base exclusively to answer this question. How we can actually incorporate self-RAG in practice in our agent. So here I have built a LangGraph agent using these techniques that I have mentioned. So first I incorporated GraphRAG for the retrieval as a retrieval tool, and also I incorporated self-RAG to basically critique or evaluate the responses of the model. So how this actually works. So first we have the planner. So this will actually plan the response to the query based on the user question, whether this question is actually just a general question that does not require a tool use. For example, if it's just like a greeting or just asking some like general question that is not related to the knowledge base, or identifying whether the question needs to be routed and directed to a retrieval tool or another tool that we have in the system. So for example, if we're asking about the capital of Germany and we want to force the model to use the knowledge to answer this question, then the planner will know that it's gonna need to route the execution to the executor node. The executor node then will take the definitions of the tools that we have and then will predict what is the best tool to use based on the user query. For example, if we're asking about the weather and we have a weather tool, it's going to direct it to the weather tool. And if we have a tool about the knowledge of Europe and then we ask the capital of Germany, it's going to route it to the knowledge retrieval tool. After the tool executes, then I have response formatter to format the response of the tool output. And then this response, that is like the formatted response, will go to the evaluation or the critique phase. So the critique node will take the formatted response and it will run it through the metrics that we just discussed. And it will predict basically how accurate the response is and whether there is any hallucination in the response. If there is a hallucination detected or the context is not enough to answer the user query, then we run the planner again and we give this feedback to the planner, telling it that, okay, there was a problem in the context or a problem in the response, and then let's execute the workflow again using the feedback that we gathered to improve the response. And then it's gonna go through it again until the critique will actually pass, give the response a pass based on the context, and then we give the response back to the user. So I have implemented that with LangGraph as I said. Let me show you the code very briefly. So here first I have the graph retrieval, as I told you. I have used the GraphRAG Python package, which is the official implementations from Microsoft. And here I have reading the index, initializing the model, initializing the embedding model for the vector search. And here I have the local search function. So the local search function, first I have also initialized the local search mixed context builder. So this one will actually help us build the context and do the graph traversal in order to build the context that we're gonna give to the LLM. And then we run the local search in case we need it. And also we have the global search. So for the global search, we have the global community context. So this will run the map reduce that we talked about. And it will basically see the community summaries that were generated by the LLM previously and see which ones that we need to select and put in our context. So now let's go to the agent implementation itself. So as I said, I implemented this with LangGraph, so it's pretty straightforward. I also gonna link the code in the description of the video. So here I first initialize the state, then I start adding the nodes. So I have the planner node, I have the direct chat, in cases when the chat is basically just like a casual chat or it doesn't need any knowledge or tool. Then after that, I have some conditional routing, so either to direct chat or the executor. Then I have the executor, whether it should call the tools or not. And then I have the response formatter to format the final response, and then it will give it to the critique. And then the critique will basically either it will route it back to the planner to refine the response based on the feedback, or it's gonna just simply end the workflow. So then I compile the graph, and it's worth noting that to run the graph in LangGraph, I use the LangGraph CLI to basically host a local server for development. And for this, you just need this configuration JSON file. So you give it the dependencies, which is the directory that contains your dependencies, like the requirements file. In this case, it's just the current directory because my requirements are in the root directory. And here I have also the graph, which is basically the link or the path to the graph itself. In this case, it's in the GraphRAG Agent Python file, and here I have the graph basically definition where I create the graph itself. And here I have the environment file just to capture any environment variables that we need during the execution of the graph. So let's see how this works in action. So let me create a new thread, and then let's first start with the casual conversation. So this actually wouldn't need any routing to a retrieval tool. So as we can see, so this is the graph representation of what we just described here. And then I said hi, it answered me without reaching to any knowledge base because that's not needed. So hi there, how's it going? So I say, give me what are the top destinations in Europe. So now it should actually route it to the executor and the tools. So let's see if that will happen. So now, yes, it have routed it to the executor. And now the executor should call the knowledge graph, the knowledge query. So the executor has, let's actually see. Okay, so the executor actually predicted that we need to do global search. So this is also an important point. We need to predict or classify the query, whether we need to do like a global search versus local search. So this is when I say top destinations in Europe, this is a global query, so we need to run global search. Whereas if I just say what is the capital of Germany, this is a local query, so we need to use local search in that case. So now the global search tool has been called, and now we just wait for the response. So now after the global search response is ready, so this is the context have been built as we've seen here, and now we have also the documents with the sources and all the destinations here, for example Germany and Italy, Finland, Spain, culture and economic hub, and now the response formatter will format the response based on the context. So it will take the user query, it will take the context, and it will then put it in the context of the large language model to produce this answer. So after that we run it through the critique. So the critique is the evaluation step to tell us like how well the response was. So retry reason, there is no retry reason. Did it address the query? The evaluator or the critique node said yes, the answer have addressed the query. Let's just take a look at the answer. So Germany, okay, Europe is filled with incredible destinations. Germany, Italy, Finland, Spain, Greece. Okay, so the answer is reasonable. Okay, we say the evaluation said the answer addresses the user query. The confidence is 90%, it's high confidence. The consistency score, so this is the consistency between the response and the context. So there is no inaccuracies or there are no mistakes or discrepancies between the response and the context. So that's why it's like a consistency score is 100%. And this response actually correctly reflects the context. So now let's go ahead and ask it to compile an itinerary. So make me a 1 week itinerary across Europe based on the. So now the planner predicts that it's a knowledge query. Okay, so the executor decided to not call a tool and directly use the context for this. And let's see whether the critique will pass. Will give this response a pass or not. So the critique is running now. Okay. So it's producing the response. Okay, so the critique have also accepted the response, and let's now take a look at the response itself. So we go here to the messages, and then we go to this response. Okay, so here is a 1 week itinerary that takes you through some of the top destinations in Europe, allowing you to experience a mix of culture, history, and modern attractions. So day 1, arrival in Berlin, Germany, travel to Rome, Italy, travel to Athens in Greece, travel to Barcelona. Okay, so now I'm gonna use a different tool. So as I told you, I have also a weather tool in my code base. So if I go to the tools here, I have also a weather tool. So this gives me like the live, it has access to live weather data. So I would just wanna assess how good this agent workflow is in calling external tools as well. So I'm gonna call the weather data. So what is, based on this itinerary as well, what is the weather in Berlin like? Okay, so here we have seen that it have used the get weather tool to get the weather, and here's the response from the weather API that we're using. And then the response formatter have formatted the response for us. So currently the weather in Berlin is quite pleasant, temperature 23 Celsius, and the critique also passed the test. So the consistency score here, it have passed. There is no need to retry. So this is what I wanted to share with you. Here's what we have implemented. So we have implemented GraphRAG integration with a LangGraph agent. So we have built a knowledge graph to build the context around our queries. And at the same time, we also have built a self-reflective agent or a self-RAG, where we also evaluate the results and the context, and we try to measure any hallucinations that might occur while answering the user query. So that's all I wanted to share with you today. I have put the link to the repository in the description. If you have any question, please let me know. Thank you so much for your time and watching. See you in the next one. Bye bye.